Welcome to this lecture on the formulation of linear quadratic regulator problem. In this video, we will define an index to be minimized. We will use the Lagrange multiplier approach. Let us consider the statement of the LQR problem in this slide. Let us consider our standard discrete plant model as given here. Let us try to find the control law UK minimizing the following cost function. Notice that this is somewhat similar to the index that we minimized in the model predictive control. Q1 and Q2 are symmetric matrices to be selected. We would want some states to become small. We may not require all the states to be small. However, we will also state that U has to be kept small. We will see the implications of these requirements shortly. Let us first discuss the contribution to J from the state. Let us take x equals x1, x2, two state example. Suppose in this example we want x1 has to be made 0. Suppose that we have no constraint on x2. We call it as a don't care state. We allow it to float, so to say. So in this case we could choose Q1 to be a matrix of this type where we have a non-zero entry here. All other entries are 0. So this is equal to Q x1 squared. We write this as xt q1 x greater or equal to 0 for all x, or we also write it as q1 greater or equal to 0. Notice that q1 is a matrix. In this case it is a 2 by 2 matrix. Its dimension is the same as that of the system matrix A. The number of states n in general, in this case n is 2. What do I mean by a matrix being greater or equal to 0? By this I mean this xt q1 x greater or equal to 0 for all x. Next we will consider the contribution from the control input to J. We want the control effort to be bounded. So we choose U equals U1 U2. It's important to notice, unlike in the case of x, we want both U1 and U2 to be bounded. We choose Q2 as follows. R1 and R2 are the entries in this Q2 matrix. So when I multiply this out, I will get R1 U1 squared plus R2 U2 squared. Both R1 and R2 have to be chosen as non-zero. No solution to this problem if either one of these two is taken as 0. If any of them is 0, the control law calculation will result in the corresponding control effort going to infinity. Basically it says that if any element is 0, then that control law costs nothing, and so we can take it to infinity. But then we know that no control effort can be of 0 cost, so we have to bound it. So if you allow any of these coefficients R1 or R2 taken as 0, then the corresponding control effort will be unbounded. If we don't want that to happen, we would insist that both R1 and R2 to be chosen as non-zero. So we write this as ut q2 u greater than 0 for all u not equal to 0, or q2 to be greater than 0. So we also call it as q2 is positive definite, whereas q1 is positive semi definite, because we allowed q1 to be greater or equal to 0 in the previous slide. To summarize, we considered the standard state space model to find uk, which minimized the following cost function. We want q1 to be positive semi definite, q2 to be positive definite, both q1 and q2 are symmetric. We restate the problem as follows: minimize this j subject to this equation where k is to be considered from 0 to some number 1, where this has to be minimized for k equals 0 to some number capital N. The value of this N will be discussed in a subsequent video. Let us restate it. We want to minimize this objective function subject to this equation. We will come up with a Lagrange multiplier lambda k for every k. Here is the modified objective function that we have to minimize. Basically, we have taken this original index, to that we have added Lagrange multiplier times this left hand side. We have to minimize this with respect to u, lambda and x. We do this in the next slide. J prime has to be a minimum with respect to u, lambda and x. Here is J prime. Let us differentiate. First, let us differentiate with respect to u. Notice that when I differentiate this, I get from this term the first expression here, and from here I get this lambda t k plus 1 times b, and we would want this to be equal to 0 because we would want this to be minimum with respect to u. This is partial with respect to u. Next, let us take the partial with respect to lambda. We get this expression. Lambda appears only in the second line, so I get this, and this is to be equal to 0. Now let us differentiate with respect to x. I get this expression. How do I get this? The first term comes from here. This lambda term comes from here. It comes from differentiating this x of k plus 1 corresponding to the previous k value. So we get lambda t of k from there. And we also have lambda t of k plus 1 into a into x of k. When I differentiate this with respect to x of k, I get lambda t of k plus 1 into a as given here, and this is also 0 because this j prime has to be a minimum with respect to x of k as well. So x of 0 is known, the initial state is known, but the Lagrange multiplier is not known at time equals 0. So we cannot march forward. So as a result, this cannot be solved in an explicit manner. We will show that this becomes a 2-point boundary value problem. We will do this in the next video. To conclude, we defined an index to be minimized. We explained the weighting matrices Q1 and Q2. We modified the objective function using Lagrange multipliers. We differentiated and arrived at a system of equations to be solved. In the next lecture, we shall solve this system. This brings us to the end of this presentation. Thanks for joining. Goodbye.